Hi friends, I'm Anand Panchbhat, Engineers classes, and today we're going to start with the next topic in a transformer, that is equivalent circuit. Friends, we people have understood that how exactly we model a transformer. The vector diagrams that we people have seen, in which initially we have considered an ideal transformer, we just have considered that how magnetic things are working into it and how the secondary voltage comes into existence. Then we have gone towards a little bit ideal, a little bit practical transformers, that we have considered what exactly resistive drop occurs in both the windings. Then after, we have gone for exact practical transformer, where we have also modeled its inductive drops. Leakage inductance is developed over here. I have told you, see, whenever supply is given over here, what happens? Current starts flowing into the circuit. If secondary is open circuited, still some current flows into the circuit, which develops the magnetic field. In that case, what happens? Some majority flux flows like this. Majority flux is developed in this way, but there are some, little flux, they form such loops as well. And the flux is cut by its own turn, so that's why it is developing some self inductance, and that is what is the leakage inductance. Because flux is generated, 100% flux is generated, but this much flux is not utilized. Fine, so that's why it is called as leakage flux. Fine, so this is what we have over here. And now let us talk about equivalent circuit. So if I want to talk about equivalent circuit, guys, even if secondary is open circuited, mark my words, even if secondary is open circuited, we are still drawing some current in primary, which technically builds the magnetic field. So if I want to understand that, if I want to model that in some easy representation, what will I do? I'll say that I have got a source over here, and then it is given to the transformer. But transformer, naturally, it is having its resistance and inductance. Fine, okay. And it is also having something which is generating a magnetic field. So I consider this shunting branch over here, which is giving me a magnetic field. Sir, we are not understanding what exactly or how exactly it is doing it. I'll explain. Then we are having transformation effect. This is where we are having secondary, it is having its resistance, its inductance, and then we are having this as V2. This is where we have given, which is V1. Fine, here I have got E1. E1 is converted, it is transformed to E2. Fine, when I connect load over here, what happens? Some I2 current flows into the circuit. And E2 minus I2Z gives me the value of V2. And when I talk about this, here I am getting I1 current. Fine, here I am having I2 dash current, which is due to the load. Fine, which is due to the load. And here I am getting some amount of current which is called as I0. It is my no load current. So if the load is not connected, let us consider if the load is not connected. If the load is not connected, I2 becomes 0, I2 dash naturally becomes 0, and still my primary winding is having some sort of current. So this particular circuit is perfectly modeled that way. Is it clear to all of you? Fine, any doubt till now? So we understood, basically we have drawn a transformer only. हमने क्या किया ट्रांसफॉर्मर के अंदर? भाई वही ट्रांसफॉर्मर, ये प्राइमरी, ये सेकेंडरी साइड है. सेकेंडरी पे उसका जो भी आर एल जो मॉडल करना है वो कर दिया. R2 X2 बोलेंगे इसको, GX2 बेसिकली J बोलना पड़ेगा. फाइन, सो सिमिलरली वी आर हैविंग दिस R1 and GX1 over here. Fine, this is my R0, this is my X0, GX0. Guys, अभी J नहीं लिखूँ तो भी चलेगा. It is fine if I'm writing X, but whenever I'm doing any of the calculation, you have to understand it is imaginary part. Fine, that's where you're not supposed to make any mistake. Fine, okay. So now I say this is GX0 and this is R0. So what is this basically? So again, when the secondary is not connected, when the load is not connected to secondary, but we have energized the transformer, what will happen? Some I0 current is flowing over here, which is definitely developing some losses. Fine, okay. So one loss I have, which is I0 square R1. Fine, this is the copper loss, which is fixed. because I0 is the magnetizing current that you have considered over here, fine. But you know, copper loss, when I say I0 square into R1, fine, this much, but the value of I0 is very small. That is so terribly small in comparison of the loading condition of the transformer. So when I load the transformer, fine, when I load the transformer, I2 is present, due to that I2 dash is present. So here I1 becomes I0 plus I2 dash, where when we see this equation, I2 dash is very greater than I0. फाइन. नेचुरली जब लोड आएगा तो लोड करंट फ्लो होगा कि तब जो करंट डिवाइस ले रहा है वो करंट डेफिनेटली वो नो लोड करंट की कंपैरिजन में बहुत ज्यादा होगा. इज इट क्लियर? फाइन. सो वी कैन से दैट, एंड दिस इज आई एम टॉकिंग अबाउट अ फुल लोड करंट. दिस इज व्हाट आई एम टॉकिंग अबाउट अ फुल लोड करंट. मतलब सर फुल लोड करंट का मीनिंग क्या? फुल लोड करंट का मीनिंग ये होता है कि ये ट्रांसफॉर्मर जितने केवीए के लिए डिजाइन किया गया है, फाइन, जितने केवीए या तो वोल्ट एम्पियर के लिए डिजाइन किया गया है. सपोज वोल्ट एम्पियर इज 1000 ओवर हियर, 1000 VA का ये ट्रांसफॉर्मर है, 1 kVA का ये ट्रांसफॉर्मर है, मतलब दिस ट्रांसफॉर्मर इज डिजाइंड फॉर 1 kVA. सो आई कैन से दैट व्हाट इज द फुल लोड कंडीशन? दिस इज सपोज 10 volt I am having over here. Suppose this is designed in a way it is 100 volt to 10 volt transformer. This is 100 to 10 volt transformer. This is 100 volt to 10 volt transformer. So this is step down transformer. कितने kVA का, कितने VA का है? 1000 VA का है. ये भी 1000 VA हो गया. Power remains the same. So we can say that in this case it is 100 voltage. 10 ampere current is flowing when it's a full load condition. When it's a full load condition, 10 ampere current is flowing, and when full load is connected over here, it is going to fetch 10 volts is 100 ampere it is gonna fetch. पता चला? सो जब यहाँ पे 100 एम्पियर जाएगा, उसके करस्पॉन्डिंग यहाँ पे कितना एम्पियर जाएगा? 10 एम्पियर जाएगा. सो 10 प्लस दिस विल बिकम माई I1. फाइन. सो ये 10 के कंपैरिजन में ये करंट बहुत कम होगा. पता चला कि नहीं पता चला? सो व्हेन यू डोंट कनेक्ट दिस पर्टिकुलर लोड ओवर हियर, फुल लोड कनेक्ट ही नहीं किया है हम लोगों ने यहाँ पे करंट 0, I2 0, I2 dash 0, तो सिर्फ I0 करंट आएगा, एंड दैट वैल्यू वुड बी वेरी लेस. When we'll do examples today, we'll come to know what exactly it happens. I mean, how exactly, or what are the values of these currents, right, for actual transformers. So we can say that I2 dash is very greater than I0. So we can say this I0 is negligibly small, and hence I0 square, करंट वैसे भी कम है, उसका स्क्वायर कर दो वो और कम हो जाएगा पॉइंट में अगर होगा तो. समझ पड़ा कि नहीं समझ पड़ा? सो वी कैन से दैट दिस लॉस इज टेरिबली स्मॉल, सो वी निग्लेक्ट दिस लॉस. फाइन. तो जब ये करंट I0 यहां पे जा रहा है तो वो क्या कर रहा है? इनपुट वी आर गिविंग, देयर इज नो आउटपुट. वी आर गिविंग इनपुट बट देयर इज नो आउटपुट. आउटपुट के लिए यहां पे करंट जाना चाहिए. फाइन. सो व्हेन इट इज नॉट कनेक्टेड, व्हाट हैपेंस? ओनली I0 करंट इज फ्लोइंग इनटू द सर्किट. इनपुट इज इक्वल टू लॉसेस. आउटपुट यू आर नॉट गेटिंग. सब लॉस होता है. तो कौन से लॉस यहां पे हो रहे हैं? सो यहां पे वी आर हैविंग कॉपर लॉस, which is very small, क्योंकि करंट ही कम है. पता चला? सो इट इज निग्लेक्टेड. फाइन. दूसरा कौन सा लॉस हो रहा है? आयन लॉस. आयन लॉस में दो टाइप के लॉसेस होते हैं. फाइन. हिस्टेरिसिस लॉस, एडी करंट लॉस. फाइन. तो एक हिस्टेरिसिस लॉस होने वाला है अंदर, एक एडी करंट लॉस होने वाला है. तो उन दोनों का जो भी एडिशन है, फाइन, इन दोनों का जो भी एडिशन है, हिस्टेरिसिस लॉस एंड एडी करंट लॉस, मैंने इनपुट दिया, कॉपर लॉस हो नहीं रहा है, तो मतलब कौन सा लॉस होने वाला है? आयन लॉस होने वाला है. मतलब यहां पे मुझे जो भी लॉस मिलेगा, इट बेसिकली गिव्स मी व्हाट? आयन लॉस. फाइन. ठीक है. आयन लॉस जो होता है, इट इज गिवन बाय दिस कंपोनेंट. तो वर्किंग कंपोनेंट IW स्क्वायर इंटू R0 विल गिव मी टोटल आयन लॉस. फाइन. अच्छा, यहां पे जो मैग्नेटिक फील्ड डेवलप हुआ उसके लिए भी कुछ था करंट तो फैच किया ना हम लोगों ने, दैट इज I magnetization. Is it clear? Fine. Where I0 is very small in comparison of I2 dash. This is also what we have understood. So now let's see the circuit again. So we have got supply R1, this is X1, magnetizing component, working component, everybody over here. And now this is our transformer action or transformation, what we are having over here, primary and secondary, R2 and X2, R2 and X2, and this is where we'll be connecting the load. Fine, okay. Now I just want to get rid of this. So here what is happening, I am having I2 current if the load is connected over here. If the load is not there, naturally I2 is equal to 0. So now when I say I2, when I2 is flowing in this particular branch, what is happening here, I2 dash current is flowing. And when I2 dash current is flowing like this, we can say that if I want to remove this entire complexity, what I'm going to do is, here current is I1, here it is I0, this is I2 dash, I0 plus I2 dash is equal to I1. So just to remove this, I am doing some modeling over here. And modeling, it is approximation that I am taking over here. That is, I just have connected it. So once I have connected it like this, initially I2 current was flowing, and now I2 dash is flowing into this. So I just can't write down this R2 and X2 as it is. Obviously R1 and X1 is going to be the same. But R2 X2 will not be same. Why? Because we have to model the circuit in which the losses should not get tempered. Fine. Whatever amount of losses are happening into that particular element, the same loss should occur when you do this referring or transformation. You have referred the secondary parameters into primary, so you just can't put the same values, so they would be different. I consider that they are R2 dash and X2 dash. Is it clear? Fine. Now when they are different, then you have to have a relation between initial values and the next values or new values that you've got. So I just told you that I2 square into R2, this is the loss which previously happening, fine, which is exactly equal to, now what is happening here, I'll be having I2 dash current. So I'll be having I2 dash into R2. And just now I've rubbed one thing where I have told you I2 dash plus I0, it is equal to I1, isn't it? And I2 dash is very, very greater than I0 when it is a full load condition. So we can say that I1 is approximately equal to I2 dash. So we can say that here, instead of I2 dash, I'll put it with I1. So I2 square into R2, which is equal to I1 square R2. This is R2 dash. This is R2 dash. So we can say that R2 dash, which is equal to I2 square divided by I1 square multiplied by R2. Now I know that V2 by V1, which is equal to I1 by I2, which is equal to transformation ratio K. So we have got I2 by I1. So I2 by I1 will be 1 upon K. Is it clear? So we'll be having 1 upon K. I2 by I1 is 1 upon K. This is I2 by I1 the whole square. So it will be 1 upon K, the whole square multiplied by R2. So we've got R2 by K square. That gives me R2 dash. So R2 dash is secondary resistance referred to primary. It is called as secondary resistance referred to primary, and the formula is given by this. Similarly, you can calculate X2 dash, which is equal to X2 divided by K square. Secondary reactance referred to primary. Similarly, if you want to go for transformation in a way, you are going from primary to secondary. So if you're going from secondary to primary, you have to divide it with K square. So similarly, if you're going from primary to secondary, you have to multiply it with the K square. Is it clear? Fine. Okay. So this is secondary resistance referred to primary. Is it clear? Secondary reactance referred to primary. This is square. Yes, exactly. So the losses are same. Agreed. Fine. So we have got this thing. Now again, this is I2 dash, this is I0. Just now I have mentioned that I2 dash is very high in comparison of I0, and these I1, these two currents are approximately equal, so I just can model it over here. So I can say that my further modeling would be like this. I've got my loss and magnetizing component or no load component like this, and I have got R1, X1, R2 dash, and X2 dash, and this is where I'll be having my load. So we can say that I2 dash current is flowing right now into this, but this I2 dash is approximately equal to I1, so it is fine. Modeling is okay. So we can say that R1 plus R2 dash we have got over here, fine. So we have, again, we can redraw the circuit where we are having, okay, this is R0, this is X0, fine. So we can say that we are having R0 and X0. Now we will be having R1 plus R2 dash, which is equal to R01, because everything is referred to primary, and then we are having X1 plus X2 dash, which is equal to X01. Again, everything is referred to primary, fine. So this is total resistance and this is total reactance, and hence we can get entire Z01. We can get entire Z01. Where am I supposed to write? I'll write it here. That is fine, I guess. So Z01, which is equal to R01 plus J X01. So this is how we represent it. Any doubt till now? Fine. Now there are further derivations that how we can go from Z01 to Z02. Fine. So Z01 to Z02, if you want to go, you're basically going from primary to secondary. So you have to multiply it with K square. Fine, you have to remember that thing. Okay, fine. Any doubt on this? Cool.